Hello, everyone, and welcome to this lecture series on the microassembly language. So in this series of lectures, what we're going to learn is how to write assembly language. And what you need in order to follow along with this course is, first of all, preferably Windows operating system on your machine, although Linux might work too, because what we're going to be using for this course would be the GERD's AVR simulator, which is available free online. You can just Google it and find it, or you can use this link. And what we're going to be doing throughout this course is we are going to learn how to write assembly language meant for microcontrollers. And we're going to use only simulation in order to learn how to make assembly language work and all the ins and outs of writing and creating assembly code. Okay, so what you need other than that for this course is also some basic knowledge of programming, such as a course on C or Python, so that you know what are functions, what are variables, how do you call functions, what is a main module, and so on, right? You would also need basic knowledge of digital logic, such as binary number representation, hexadecimal numbers, decimal numbers, and how to convert between these methods, as well as some basic knowledge of transistors and logic gates. However, most of that we will be reviewing during this course as well. And lastly, you do also need a desire to learn assembly language. So let's get right to it. We are going to begin at the really basic level, which is basic definitions, right? So let's start with what are computers. So computers are machines that take in data and perform some kind of computation or process on it and transform it into output data. And so the process part is called a program. So here's an image of that. There's a good representation of a computer, because computers are basically consisting of devices which will perform some operation depending on whether or not electricity is flowing through them at the particular moment, right? So computers generally have two parts: hardware, which is relatively fixed and cannot be changed that easily, and also software, which can be more easily altered by writing code, right? So digital computers understand only one language, and that is binary language. So it's known as machine code, and what it consists of is just zeros and ones. So 0 represents 0 volts in voltage and also false in Boolean logic, and it's usually represented by the number 0. And then 1 is the binary number 1. It can also be represented in Boolean logic by the value true, and it can be represented as a positive about 5 volts, positive 5 volts. Okay, so whatever language we write our code in, whether it's C or Python, some other language, or assembly code, in the end, for the processor to be able to carry out the functionality, it would need to transform it into binary data. Okay, so that's what's important. So now, how do machines think? Now, machines need two things in order to perform their task. First, they need an instruction, and then they need data. Okay, so instruction are, for example, if you have an addition process, so you say add value 1 to value 2. That is an instruction. So the computer knows how to carry out that instruction. But it also needs a second thing. It needs data. And what is data? Data is value 1 and value 2. So it needs both those things in order to perform any computation. Okay. So the machine code is, of course, series of zeros and ones. However, for us, we write the instruction in a higher level language, or we can also write it in assembly language. All higher level languages get translated into assembly before they can be compiled into machine code, which can actually run on the computer. Okay, so what are the main components of a computer? So a computer is also known as a central processing unit, CPU. So we will use those terms interchangeably. And A computer is also a processor. It can be called a microprocessor, microcontroller. We're going to look at the differences of these different terms that we're talking about as we go along. But basically, all of those terms can be used interchangeably. They are basically the brains of the computer. So 3 elements to a computer. The first one is a processor, which performs the computation. Second is memory, which stores both the instructions that are used by the processor to carry out the computations and the data that the computation is performed on. And thirdly, input and output devices. Okay, and how do they communicate with each other? Well, they need buses. And what are buses? We're gonna look at later on. So a digital computer, you can see that CPU can also be expanded into this diagram, where the CPU, central processing unit, consists of 2 main parts. The first one is a data part, and the second one is the control unit. So what does these 2 terminologies mean? Because you will see them in a lot of computer-related diagrams and such. So data path is the path that the input data takes in order to be transformed into the output data, right? That's a data path. So you can imagine a processor, and a processor can be like a city where you have data traveling on the roads. So each vehicle can be a data, and it travels through the road, and it starts at some destination, it's somewhere, and then it gets transformed or arrives at the final destination or the output, right? So how does the data get transformed? It has to go through the data path. And how does it know where to go or when to go and so on? The control unit decides that. So the control unit is like the traffic lights in the city. So they will turn on and off or turn red and green for different data at different times, depending on some kind of organization or logic, right? So all of the data is allowed to travel through the city. However, in order to keep order and not to jumble the data, they must follow the traffic protocols. And so green light, red light, green light, red light, and they must wait in a queue until they can get to the destination. So that's control unit and data path. And then of course we have memory, which consists of instructions and data, and then the input output devices such as buttons and LEDs at the most simple level, and then keyboards and monitors, microphones and speakers. And of course the internet can both be a source and a destination of data, right? So how computers work, they follow 3 principles. They follow the fetch, decode, and execute function. So how does that work? Firstly, you have instructions in the memory. So we have to do instruction fetch. This is kind of like when we have to work for money. So we are fetching the instruction. Once you have fetched the instruction, you need to decode it in order to know exactly what to do. So part of that instruction might be a control signal, and another, or can be transformed into a control signal, and another part might be a data. So then we will decode that instruction into multiple parts and then send them throughout our processor city to perform the tasks that they need to do. Whether it's data or whether it's a control signal, it gets transformed into that. So that is the decoding process of the instruction. And then finally, there's execution. And what execution means is performing the computations that are needed. So if the instruction is add value 1 to value 2, we will first fetch it from memory. So we fetch that instruction, we bring it into the processor, and then we decode it. So we know it's an addition process. So activates the calculation unit to perform addition, not subtraction, not any logic operation, not multiplication or division, but addition. So that's one part. And then another part is fetching the values or decoding values 1 and 2. Where are they? How to get them, make them arrive at the calculation unit. And then finally, the execution is actually performing the calculation and then sending the output to the appropriate channel, whether it is to store into memory or to output it using an LCD screen or LEDs and so on. Okay, so those are the 3 parts of how computers work. And finally, for this lecture, let's talk about the two types of computer architecture. So there are two. One is called the complex instruction set computer, CISC, and the other one is called reduced instruction set computer, RISC. Now, what are these two architectures? So they are, as the name represents, two different ways to create a computer. The first one, which is called CISC, is a more complex method where there are certain features there. It has way more instructions. Our more complicated laptops and workstations and servers use CISC architecture. So there are a lot of instructions, and they are of varying sizes and varying time lengths to be performed. And they might require a lot of time to perform a single instruction. And then they are complex, meaning that you don't actually have to fetch data and fetch or store data separately with an instruction. If you say add value 1 to value 2, it knows that this includes fetching value 1 and value 2 from memory, performing the calculation, and then storing the output back into the memory. And then it also has a large set of instructions. On the other hand, RISC, reduced instruction set computers, are much more simple. They have a very simple ISA, instruction set architecture, and they only have a few instructions. They don't have as many instructions. The benefit of them is that most of the instructions get performed in a single clock cycle. That means the length to perform any instruction is about the same. And therefore, when you have all of the blocks are the same size, then it's easier to pipeline them, it's easier to implement them, it's easier to optimize them, and it's just easier to carry them out, right? Problem with that is that there are such few number of instructions that you will have to tell the computer how to do everything step by step. So if you want to do add value 1 and value 2, you actually have to write 4 lines of code. First one is fetch value 1, second one is fetch value 2, which is load instructions. Then you have the add value 1 to value 2, and then you finally have a store output instruction. So instead of just one instruction, you need 4 instructions on RISC. So those are the two architectures. Now we will talk about the difference between von Neumann and Harvard architecture in the next video.